and we're going to do a little presentation here on wave, sound, and light. All right? So I've tried to get for all ages some of the explanation. The older folks will get it, and all the demonstrations, I hope, will be something that'll help you understand more about wave, sound, and light. The very first question we have is, what is a wave? You know what a wave is? Anybody? What? Ooh, that's good. Sound waves are a great example of a wave. Water wave, you ever been to the beach? There'd be no fun without waves, right? Yes, in the ocean. Light waves. There's all kinds of waves. A lot of people can tell us what a wave is, examples of waves, but what a wave is, most people really don't know what a wave is. All right? It's all about energy. It all gets back to energy. Okay? I'm going to throw this to you, okay? Will you catch it? It's sponge. It won't hurt you. All right. Now, it's really lightweight, but did you feel anything when it hit your hand? Yeah. If I'd thrown you a softball, you'd have felt more, wouldn't you? And if I'd thrown you a bowling ball, you'd duck and let it hit him, right? Okay? A lot of energy there. That's one way energy gets from one place to another. You have to have an object, you push on it, and it carries the energy like a mailman. But not all energy goes that way. Some energy just doesn't attach itself to anything. It just goes through whatever's between me and you. Is everybody hearing my voice? All right? Well, sound energy, a sound wave, that energy just goes through the air. And as it goes through the air, it moves the air back and forth. And it's that movement, it's that disturbance, that pattern of disturbance that actually is a wave. Okay? Every wave, whether it's a light wave, whether it's a sound wave or an ocean wave, no matter what kind of wave it is, all waves are created. They're made by something vibrating back and forth. My vocal cords are going back and forth. You can't see those. This is a tuning fork. It makes a sound. Everybody hear that? Okay? That tuning fork is going back and forth, back and forth, back and forth, back and forth, back and forth. In fact, it's going back and forth 256 times every second. Can you see it go back and forth? No. You know why? Because you got human eyes. Human eyes, humans, we see something for a very long period of time. We hold on to that image. But, touch it. Is it vibrating? Can you feel it? All right? Yeah, it's hitting against your hand 256 times every second. We call that a frequency. Here we go. Ooh, wiggling it, isn't it? That's how fast it's wiggling. Okay? So no matter what kind of wave it is, you got to have something going back and forth, back and forth. Now, all a wave is energy going through something, making whatever it goes through back and forth. Now, I've got, this is another tuning fork, and it's identical to this one. It doesn't look like it, but it is. Okay? So if I hit it, it sounds just the same. Now, what I'm going to do, I'm not going to hit that one. I'm going to hit this one. And when I hit this one, it's going to send the energy out in all directions. And as it goes through the air in all directions, since it's going back and forth 256 times every second, it's going to make the air in the room go back and forth 256 times every second. And then your eardrums will do that. And that's why you hear what you hear. Well, if the air next to this one starts moving back and forth because of this, it'll make this one start to work, even though this one wasn't touched at all. Listen. Now, I'm going to get this one started, and then I'm going to grab it and stop it. See if that one's not working. No, that one's not. Didn't even touch it. Kind of like magic, but it's not. It's just showing you that a wave is just energy going through whatever it's going through. In this case, it's what?
It's science.
It's science. It is. Good.
Every magic trick has a scientific solution behind it. Other than that, it's just an illusion.
Every one of them. That's right. Now, for you younger people, you have no idea what this is. This is a record. Okay? Yeah, us old people, that's what we do. That's how we used to listen to music.
I've listened
okay?
to one or two.
Yes, and they're a little scratchy, but this has a groove cut in it. Okay? And so when the people are in the studio, and they used to say cutting a record, and what that they would sing in the microphone, the instruments would, all those sound waves hitting the microphone go together to make one sound wave. One sound wave. Looks kind of funny. And so when they cut the record, the needle that was cutting the groove actually cut that sound wave, that pattern, into the wall. So if you could look at this under a really high-powered microscope, instead of a smooth wall, you would see it kind of sculptured. And that's the sound wave, all right? So if you can get that back, you recreate the sound. Now, I'm going to get it spinning, but I'm not going to put a needle. I'm not going to put the needle to it. This is just a piece of construction paper that I curled up into a cone. Now, I'm not going to tell you how old I am, but I am on Medicare. So, back when I was your age, there was a gentleman on TV on Saturday mornings named Mr. Wizard. He was on CBS, black and white, and I watched him every Saturday morning because we didn't have science museums back then. And this was one that he did that kind of got me started on something. This is a sewing needle, just like from your mom's sewing box, okay? And so I stuck it into the paper, and so I'm going to let it ride in the groove. And as it rides in the groove, it won't ride smooth, it'll vibrate because it's going along with the wall. And as it vibrates, it's going to make the paper vibrate. And if the paper vibrates, that's going to push the air, and the air is going to vibrate. That's going to be your sound wave. It's not real loud. All right? And it skips a little bit. I'm just going to put it down somewhere in the middle, and you should be able to hear it. That's pretty cool, isn't it?
Yeah.
No electronics, no amplifiers, no wires.
That's neat.
You know, you couldn't see that the tuning fork vibrate back and forth, go back and forth, but you can see a speaker go back and forth. And so, and I'm going to start off. This is going to vibrate back and forth 2 times a second. That's what we call frequency. You know what the word frequent means? How frequent? How often? How many times does it happen? Okay? So that's what frequency is. How many times does whatever's vibrating, the tuning fork, my vocal cords, the speaker, how many times does it go back and forth every second? And I'm going to set it on 1. And everybody can see that going back and forth 1 time every second. So you can see that, not 256. You can see the 1. Now if I go to 4, a little bit faster, can you see that? Okay? You can see it, but you can't hear it. Because the human ear doesn't start working unless the sound is at least 15 times a second. I'm going to turn it up to one that you hear a lot. That sound right there, that's 60 times every second. And so if your refrigerator's going, that's what you hear. If you got a light that's making a noise, that's what you hear. Because our electricity is powering it 60 times a second, so to speak. So that's what you hear. Now, I'm going to keep going up. That's 100 times a second. And so every time it's a different frequency, it goes back and forth a different number of times, your ear hears it differently. If you've ever been in music, it's called pitch. 200, 300, 400, 500, 600. Oh, some of you are covering your ears already. 700. And it only goes to 800. My little thing here only goes to 800. Man, that's hard on your ears, isn't it? Guess what? Human ears can hear all the way to 20,000. Think how irritating that would be. Okay? Have any of you ever heard of these ringtones for cell phones that teenagers can hear but your parents can't hear? Okay? I don't believe it. Don't believe it. Most of your parents can hear that. Your grandparents can hear. Okay? As we get older, our eardrum gets less flexible. So instead of hearing 20,000 or 18,000, like I'm down to about 12,000, I'm really normal. That ringtone's about 12,500. So if you got a teacher that's young, she can hear that. Don't try it, okay? Most of the parents in here can hear that. All right? So that's the way that works. By the way, talking about hearing, we measure how loud it is, not what frequency, but just how loud it is, in something called dB, and that deals with the energy that's in it. Well, if I hit this, put a little energy in, I get a little energy out. If I put a lot of energy in, same sound, but it's louder. Okay? Now, if you have any kind of a music player that you use with earbuds, an iPod or MP3 player or whatever, okay? If you turn it all the way up, you are destroying your hearing. I'm going to tell you that. Now, all of you are young enough that you don't have to do this. You haven't done enough damage. There's little hair fibers in there that won't grow back. And the research is showing now in the past 10 years that a lot of our teenagers are losing a lot of their high-frequency hearing, which affects how they can hear. If you turn all those up 3/4 of the way, you're within the safe zone. But if you go past 3/4, you never know it because it doesn't hurt. But parents and please, don't do that. It really does make a huge difference. Okay? I'm going to speak this down. I'm going to bring something else. This one over here. Okay. So what does a wave look like? That would be our next question that we want to ask. What does a wave look like? And you've described it very well. Okay? Let's see. Come on over here. All right? Come on over there. I need somebody to have a tight grip. Right about there. Okay? Now you need to hold on with two hands because it slips out of your hand real easy. And so I want you to hold on with two hands because if it slips out, guess where it's going? Okay. All right? All right. Now you hold your hand still. There's no wave in the spring because there's nothing vibrating to send energy into it. Okay? So I'm going to move my hand up and down. I'm going to make it go up and down. That's going to send energy through the spring. And as it goes through the spring, it's going to disturb the spring. That's what we call a wave, that disturbance. All right? And so, that's what you were talking about, isn't it, young lady? Isn't that what you were talking about? All right? Now, that is exactly one wave. Because a wave has two parts. It has a hump and a bump. Okay? Now, when you get in science class later, they might say a crest and a trough. If you go to dental school, they'll say a crest and a cavity. But anyway, all right? So you got one wavelength. Now, let's say that there's, let's just say there's 10 feet between us. This wave is 10 feet long. So if I wanted to describe you, I might say, well, you're 4 foot high, you weigh 100 pounds, you got brown hair, you got blue eyes. But with a wave, we talk about its frequency. How many times is the vibrating thing going up and down, and how long it is. All right? So it's 10 feet long. Now, there's a neat rule, and this happens for all waves, sound waves, light waves, everything. Watch what happens. My hand, by the way, was going up and down 1 time per second. So 1 time per second gives me that long of a wave. Watch now. I'm going to make my hand go back and forth 2 times a second. Okay? All right. So now my hand's going back and forth 2 times a second. So start in his hand or start in my hand, measure out 1 hump and 1 bump, you're only halfway across. So if the frequency goes up, the length of the wave goes down. If I can make my hand go back and forth even faster, what would happen to the size of the wave, how long it is? What do you think? Anybody? It gets shorter. Now, I'm human, and humans can't keep their hand going at a steady pace much more than about twice a second. But I've got a machine that can do that. Thank you.
Thank you for doing it
Well,
the
you're
second
welcome.
time, 2 times per second that way, because I didn't see the first time. I wanted to see what it looked
Well,
like.
you're going to see this one even better then, okay? This little device here is nothing more than a speaker turned up this way with a little device I can put a string to. And so I can make it go up and down whatever I want. And it turns out that if I shake it up and down on this end 9 times per second, so it's got a frequency of 9, that's one wave. All right? Now, it looks like there's 2 sections, but when this half is up, where do you think that half is? Down. And when this goes down, what do you think that half does?
Up.
Yeah, so you always got one hump and one bump. So I've got a frequency of 9, and that's my wavelength there, and that is about 10 feet long. So what's going to happen if I shake this up and down faster? What's going to happen to that length right there? Well, this is going to go faster, right? But is it going to stay the same length, or is it going to get longer or shorter? What do you think? I go to the opposite, shorter. Right, watch. Now I'm going to go to 18. Now remember, I've got 2 pieces there, 2 sections. That's one wave. I'm going to go to 18. What's 4? 1, 2, 3, 4. So 1, 2, I'm only halfway across. This is just like we were doing. Okay? I can go up even more. I'm going to go up to 36. Every time I shake it up and down twice as much, it gets half as long. Okay? So now I'm only there to there. Let me double it again. Okay? I should get 2 right from there to there if I double it again. What I do? Okay? You notice it gets smaller and smaller every time this way. So if I double it again, it would cut in half, but you couldn't see it. It'd be so tiny. Okay? But I do want to do one thing that's kind of special. I'm going to go back to shaking it up and down 27 times a second. Let me get it just right. All right, 27 times a second. What that means is every piece of that string is going up and down 27 times every second. Okay? If we could turn the lights in this room on and off exactly 27 times a second, the coolest thing would happen. Well, this piece would be here, this would be here, this would be here, this would be here, and then the light would go off, and each piece would go down and come right back where it was when the light came back on. And then it would go back off again. So in other words, it would look like it's frozen to you because you're only seeing it in that one spot. Now, we can't turn these lights on and off 27 times every second, but I have a strobe light, okay? Now, I'm going to shine the strobe light this way. If anybody has a problem with a strobe light, you can either just close your eyes for a minute or turn the other way, but I'm not going to point it out this way, okay? But I'm going to ask you to turn those lights off in a minute. Now, a strobe light is a light that I can make it go on and off however far I want. I'm just going to turn it on at any old rate, and then I'm going to keep changing it, and you'll know when I get to change. All right, everybody see the string? All right, I'm going to keep changing it. I'm going to keep changing it. I'm getting close. I'm changing the light till I get down to 27 times a second.
Gonna be over, Mommy?
Okay.
Okay, that's fine.
Okay. All right. Now, if I had two of you running across the room and you arrived at the same place at the same time, what would happen to you? If you bump into, would you keep going the way you were going?
No.
Would you keep going the way you were going? No. See, but y'all are made of particles. When waves go through the same place, they don't affect each other.
No.
But the place they're going through is affected. In other words, it's changed. If two sound waves are going through each other at the same place, they can either make it louder or they can make it less loud. It's called interference. I want to show you a neat little demonstration here with that. This is a radio. Everybody fairly familiar with those. Unlike the record player. Okay. And I'm going to make it go through this real cheap little speaker that I've got here. It's $2.95. You do get what you pay for. All right? It doesn't sound very good. And I want you to hear it. Pretty terrible sound. Part of it's because it's $2.95. But part of it's because, have you ever noticed that when you have a speaker, it's mounted in a door, put in a box. You don't see the front and the back because it's sending waves out this way, which go around, and it's also sending waves out the back, which go around, and they're exactly, if this one's pressing, this one's spreading out. So when they go through each other, they take each other down. They make the sound not very good. It's called destructive interference. So you always block off one side. Doesn't make any difference which side you block off. So I'm just going to block off one side. Okay? I'll block off only the front of the speaker. Quite a bit better. Or I can block off this way. See the difference? That's why your speakers are always in some kind of a box or mounted or whatever. It's to keep the interference, to keep the waves in the front from messing with the waves in the back. That works a whole lot better. Okay? Okay, we've been talking a lot about sound waves. Let's do something with light waves. What's your name? Gina?
Jenna.
Jenna? Jenna, come on, Jenna. They're big, but they're not very good. All right, this is a regular light bulb, okay? Okay, come on, turn around. I want you to face them, okay? Come on around over here. We've got to back up just a little bit. This is a regular light bulb. Now, it's not, the light bulbs you have at home are a little bit smaller, and they've got a white coating on them, don't they? Okay, they're not clear. That white coating's on there to spread the light out more evenly so that you don't get shadows and things, okay? But this is clear, and so the way it's supposed to work is you put it in a lamp and turn the switch on, right? And what happens is, there's little things, parts of an atom called electrons that run through the wire. See that wire there? It runs through the wire, and that generates light eventually, okay? Well, when you turn the switch on, it gives it a push. It gives the electrons a certain amount of push. Everything in your house gets the same amount of push, okay? Now, there's a gas in that bulb, and what we're going to do, we're going to push those electrons much, much harder, almost 100 times more than the lamp would, and the electrons are going to leave the wire and come to your hands. And they're going to go through your body into the earth, which means they've got to go through that gas. Guess what happens when electrons go through a gas? You ever seen lightning? That's what's happening. So we're going to kind of create lightning here, okay? So what I want you to do, I want you to hold it like that. 2 hands, both hands, okay? All right? And let's put it right here so everybody can see. All right, so hold it down like that. Now instead of putting it in a lamp, this gives me a lot of push. All right, more than that light switch will. Let me just make sure it works. Let's see. Oh yeah, that's a whole lot of push. Okay. All right. For you parents, you got 120 volts at home. This is like 16,000. Okay. No problem though. 9 out of 10 students never feel a thing. You're the first one. Your odds are really good. Okay. All right. So you just hold on. All right. And move your hands back a little bit so people can see more. There you go. Because what's going to happen? Those electrons are going to leave the wire, go through the gas to your hands. But when it goes through that gas gives off purple light. So just little streaks of purple light to each of your fingers. Okay? Ooh. Everybody see that? Yeah, now if you move one of your fingers around on the bulb, it'll follow your finger. Just move one of your fingers around here. Yeah, it follows your finger. Okay? And that's all this, we're treating that bulb into making light that it's not supposed to make. Alright? So we had to push the electrons awfully hard. Okay? Alright? Alright. Thank you so much. How about you? What's your name? What? Benedict? Come on up here, Benedict. All right. You ever seen a bulb like this? Yeah. Yeah, this is that's the kind of bulbs that are in there. They've been around for a long time. Okay, they're called fluorescent bulbs. There's no wire in there to get hot. You ever notice a regular light bulb, it gets hot, doesn't it? It gets really hot, okay? Well, this one doesn't have it in there, but it's still, you got to push electrons, but there's a gas in there. Kind of like what we just did with that bulb, all right? So, I want you to hold it like that. You're going to stand right over there. Yes, put your hands together. Okay, put that hand together. There you go. Okay, all right? Now, when you put it in a fixture and turn the light on, you get a push, and it pushes the electrons through the gas, and it makes light, just like we made light just there, okay? Except, of course, it's white light, but I'm going to push it with this. Now, we know it's going to work because it worked with the last one, all right? It doesn't need that much push, but I'm going to do it. I'm going to put mine on, too. Okay? Yep. You got it? All right? Okay, now, if I just did that, we know that's going to work. So I'm going to do this. I'm going to hold on to this. And as this goes up in voltage, I'm going to go up in voltage. Okay? So, that's why I've got that. Okay? All right? So, I'm not even touching it. I just have to get close to it. Or like, when I get, just around my wife, she just glows. Okay? All right? Now, Benedict, if you'll let go of your end for a minute, I'm still able to push them down there. May the force be with you. Okay? All right, you got it? All right, I'm going to let go. Turn the lights back on. Okay? I'm going to let go. All right? Because I have to go downstairs since I went up. This is not the easy thing to do. Okay?
Did it hurt?
No, it doesn't. But it's kind of a funny thing, though. Most men can hold on to that, and most women can't. and it has to do with body chemistry. A woman's body chemistry is a little more charged, and it just zaps you pretty good. I have to tell one yet. Okay, we've got one last one, and I kind of saved the best one for last. But here's what I got to do. I got to clear out a path here. See those three little things right there? I'm going to move a table right there. So if you do one side or the other, you're okay. But right in there. Okay, you just move over there.
Just come to hold it for a minute. I will. Tell them just slow down.
Hey, Doug, we actually have someone that is going to take you. If you can slow down just a little bit so she can shoot you.
Okay.
Well, kind of shoot you.
All right.
With a camera, Doug.
With a camera.
Okay.
I have one.
Okay. Well, have you learned anything yet?
Yes.
All right. Okay. This is I have a lot of students who make this at home. This is just a cylinder. It could be a cardboard tube. This is a piece of PVC pipe. I've made them out of green bean, big can of green beans. I took the green beans out, and it's got to be open on both ends, all right? And on one end, I just took good old saran wrap, Glad wrap, some kind of, clear kitchen wrap, and stretched it really tight. It needed to be really, really tight, and that's all it is. And then there's a little piece of mirror. I took a piece of broken mirror. I took a little mirror and I put it in a towel and I hit it with a hammer and I picked out a piece that was just right, and I super glued it right on somewhere around the middle. That's all it is. It's just the simplest little thing that ever was. Okay. And I've got it sitting in a piece of sponge rubber so that the vibrations in the room won't bother as much. And on the back side, it's open. So, because what we're going to do is we're going to put sound waves through there. Okay? Now, let's think about what we've learned today about sound waves. Sound waves, something's vibrating like the tuning fork, am I right? Or the speaker. And when it vibrates like this, then as the energy goes through the room, the air vibrates like that. So, I've got a speaker here, and we're going to play some music through it. And so the sound, the waves are going to go through here, and it's going to make the air do that. And then when it finally reaches the food wrap, it's going to make the food wrap do that with exactly the same frequency as the speaker, as the music. So now, it's got a mirror on there, right? Okay, so I've got a little laser pointer right here, got a little laser pointer, and I want to point it at the mirror and bounce it off the mirror onto the wall, okay? So that's what we're going to be looking at, is the wall. And that's all there is to it. And so depending on what kind of music you play through it, that's what, and I picked out a piece of music that'll give you some good patterns, all right? When you hit the right number of vibrations every second, you get a pattern. And if you get a different number of vibrations, but it's a multiple of that, you get a different pattern. And so this gives us